the effects that substituents will have on electrophilic aromatic substitution. And there's two types of, I guess, substituents that favor ortho and para, and substituents that favor meta directions. So let's just talk about the ones that favor ortho and para. So these tend to be at least some type of structure that has lone pairs for resonance stabilization. So that green has lone pairs for resonance stabilization. So what would be some examples of compounds that kind of fit this description? Well, as we talked about earlier, the NR2, NR2 is a really good at ortho and para, as is a OR group, because of those two little lone pairs that it has on there. Halogens are good examples of this that favor ortho and para. Despite slowing down EAS substitution, they still favor the ortho and para. So I guess the way that I would explain this is just to kind of draw out the resonance structures, or draw out the structures that you have. So say for example, I have, and I'll use NR2, but it could be either one of these that I've listed up here. So say I have an aromatic compound, and everyone uses benzene. There are other ones out there, but everyone uses benzene. And so let's just say that I have a NR2 there with two lone pairs. There's my hydrogen, and I go ahead and react this with, I don't know, I won't even draw out a real life example. I'll just use like an abbreviated example for an electrophile, and red. It's going to be attracted to that. And so when that happens, what do I get? Well, especially if it substitutes at the ortho position, especially if it substitutes ortho to the NR2, well, I hope you can see that I can very easily stabilize this carbocation by moving that lone pair that we have here down there. And in doing so, I'm going to stabilize it. So I'm trying to get used to this pen here. You get from having that compound there. This makes this much more stable. So obviously ortho does this. So this was up here that I just drew, was the ortho example here. And I'll go ahead and just circle that up there. Whole thing there. And then the next one I'll just draw down here would be a para substitution example. So what's another way that I could do this? Well, I could substitute this with para with regards to, say, NR2. And so I'm going to go ahead and just draw this step here after we've added the electrophile, just to save some space. And let me just fill in these things here. So I went ahead and just drew this out in advance to save time. But I went ahead and drew the electrophile adding in a para direction and a 1,4 direction, and I have my carbocation here. And while you may be thinking, well, there's no way this lone pair can stabilize that carbocation from over there, remember that these all exist in at least 3 resonance structures that I can draw, which gives us a really nice stabilized resonance hybrid. So what I can do is I can move this pi bond here, and in doing so, what I will get is I get this carbocation that's again underneath that lone pair, or within shot of that lone pair, to move that lone pair down there, and we get a very, very stabilized structure. So I'm just going to go ahead and draw that R2 in. That has a positive formal charge. Okay, so that's the para reaction there. Or if we had para substitution, that's what it will look like. Now, one of the things that really threw me off whenever I was going through this is that this is not an aromatic compound, but neither is this carbocation being there. Is that an aromatic compound? None of these are aromatic, quote-unquote, compounds. Anytime you form that carbocation, it's not aromatic anymore. But what we're doing with this is we are stabilizing that carbocation. Remember that resonance structures exist as hybrids. They don't exist in one conformation or the other. They don't morph back and forth to the other. They exist as what they exist as. So things that tend to be favor at least meta, and I'll go ahead and just write out that ortho is 1, 2, para is 1, 4. I hope that's review to you. The things that favor meta, that favor substituents at the 1 and 3 position, the reasoning behind that is, at least to a large extent, because of the same thing here. Now remember whenever I talked about nitration reactions and you get this really weird water leaving group that plops off and forms this nitronium ion, that's the only time you're ever going to have positive charges that close together. So I'm just going to go ahead and draw out the meta, I guess, substitutions here, or examples of each of these, but I'm going to go ahead and draw like a chart on the next page. Totally ignoring the ortho and para side of things. We're just focusing on meta. And if we're to talk about what makes a good meta, I guess, inducer is, I'll just go ahead and put this right here, that this is any substituent that does not have lone pairs. And I'll just write that. That's an R. Any substituent without lone pairs. Without lone pairs is a meta director or a meta substitution. And I'll explain what I mean by that whenever I'm saying. So if we were to just kind of, any substitution we have that without lone pairs. So I'm going to go ahead and make a little, I guess, short thing here. That if we over here we have unstable molecules, and down here we have a stable molecules. So if we have substituents that don't have lone pairs, and we're going down this list here, so up here I would say like there's ortho. That's really unstable. Then there's para. And then just a little bit lower, it's not like significantly different, is a meta. And that these are very slow. Meta directors tend to make EAS reactions really slow. But let's, I guess, clarify this. So the poster child of a meta director is not only NO2, but I'll just use NR3 because I feel like that would drive home my point a little bit more, and it's going to have a positive formal charge. So let's say that we already have a NR3 attached to our aromatic compound. There, and there's NR3. Now, this already has a positive charge. Hope you can see where I'm coming from with this. So let's say that we go ahead and we just run this reaction with a generic electrophile. And let's say we do ortho. I'll just write that up here. That this is the ortho example. If we do this, what are you going to get whenever you do this reaction immediately? Well, say that it, you know, it doesn't really have to be that one, but if we're adding ortho, then it has to be this pi bond's going to come out and try to grab that bad boy. So if you do this, though, you're going to get something that should scare you up a bit. So N plus, I'm just going to put the R3 over here just so we can see it better. There's an electrophile there. There's a hydrogen there. And you have a positively charged carbocation. I don't know if you remember whenever we talked about nitration reactions, but you will never, ever, 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 ever do this. So this right here, these two positive formal charges so close to each other is bad, which hopefully that's not news to you because positive charges don't like to be close together. They don't like to be close together more so than even electrons don't like to be close together. So that's what happens when you do ortho. Now let's see what happens if you were to do para for the same thing. So we have some generic electrophile, and let's say that it adds to the para position. Oh, where's my red? Right there. So this pi bond reaches out and grabs him. So that you may be thinking that when you substitute it from this, well, that's kind of far away. It's on the opposite end there. But you need to remember that this is always going to exist in resonance. And when you resonate, one of the things that you could do is, well, let's just say that I move this lone pair or this pi bond there. Hopefully you can see that I'm putting it to that one there. If not, I'll just draw it over here. So you end up resonating your molecule, and I hope you can see where this is going. It's gonna be bad. The other way that you can do this is to move that there, which gets us back there. So both of these, this is just as bad as this. I hope you can see that. But this is still, it's still kind of bad. And even if I were to move, you know, whatever, there are obviously other resonance structures I could probably draw for this. I could draw a third one if I wanted to. But I hope you see that these are also, even then, that's still pretty bad. Bad. And then this is just as bad as that guy up there. So let's just draw it over here in the corner if I got room for it. What would happen if I were to draw this reaction and then substitute at the meta position? So again, I'm going to skip the reaction here. I'm just going to show you what happens if we add the electrophile meta to the NR3 group. So there's your NR3, it has a positive formal charge. And if we add meta, there's your electrophile. There's your hydrogen. Okay? So we have this here. Whoa, we have that guy there. We got that guy there. And oh, yeah. Look at that. Hot damn. It is now as far away. The two positive charges are as far away from each other as physically possible. Yeah, okay, so that's awesome, right? That makes us happy, right? Because that way they're as far away from each other as physically possible. Ortho is bad, para is worse, and then meta, it still sucks because you have that positive charge there, but it's so far away that we tend to favor that, especially for a substituent that is without lone pairs. So